Let's revise the actin-myosin bridge cycle quickly. This is in a relaxed state. As you can notice that the titans are uncoiled and the actin fibers aren't attached to the midline. The first step is the cross bridge formation. Okay, you have the thick filaments and you have the thin filaments and the myosin head, and you have two molecules of ATP and phosphate, one phosphate molecules. For the cycle to start, the calcium molecule will switches the machinery on, and the myosin head begins bind to the actin. تبدأ السايكل إنه ذرة الكالسيوم راح تبدي العملية أو تبدي يعني المكنة مع الدورة، إنه الجزء اللي هو المايسين هيد راح يرتبط بالثين فيلامنت اللي هو الأكتين. Let's assume movement occurred or a force is applied to changes from its resting state or relaxed state to its contracting state. What will happen? The myosin head will move, okay? While binding to the actin, it will move. By this process, the stored energy, which is the ATP and phosphate, will be released. By the chemical formation of the ATP and phosphate, they will bind to each other, which will create ATP. انطلاق الذرات ال ADP اللي كانت مخزونة بالمايوسين هيد بتفاعل كيميائي معين راح تعطينا ذرات ال ATP. ذرات ال ATP راح تتحرك وراح تبعد مكانها على المايوسين هيد. Of course, the movement of myosin head will be in a elastic bound, not elastic, in a bounce movement. It will bind to the actin and unbind, bind and unbind, and so on. This will need energy. The energy is provided by ATP. Once the head is detached, من راح ينفصل المايوسين head عن الأكتين؟ راح تنفذ عملية اسمها ATP hydrolysis, which means the ATP will lose one phosphate molecule and will return to its original ATP. Once the myosin head deattaches, of course we said the movement of myosin head, it will go up and down, up and down, up and down. This will need energy. So, of course, all of these happening in the parts of a second. Okay, so once the head of myosin goes down, the energy is broken down to its original state, and then it goes back up, and the cycle is repeated over and over and over again. We have a couple of questions. We are gonna solve them together. Length of a contraction. Four sarcomeres arranged in a series. As you can see here, we have 4 sarcomeres. 1, 2, 3, and 4. Of course, each pair from here to here is an individual sarcomere. If each sarcomere shortens by 1 micrometer, then how much will the chain of 4 shorten by? This is very easy. We're just going to multiply the shortening of 1 sarcomere by 4 shortening of 4 chains. The answer will be 4 multiplied by 1 micrometer, which will equal to 4 micrometers. A single sarcomere is about 3 micrometers long when relaxed, and 2 micrometers when contracted, and hence only shortens by 1 micrometer, because we're going to subtract 3 in the relaxed state or in the first state from 2 micrometer, which is in the contracted stage. How does this result in a shortening of, let's say, 5 centimeter in a muscle, like the human bicep brachii, which is the main arm flexure? The answer of the previous question, this one. Since each microfibril contains sarcomere arranged in series, and since all sarcomere shortens when the fiber contracts, the length change of each sarcomere must be added together. So, each sarcomere short like in the previous question, when we said if we have one sarcomere shortened by 1 micrometer, then 4 will be shortened by 4 micrometer. In the same sense of the first part of this question, for each sarcomere shortens by 1 micrometer. A series or chain of 10 sarcomeres will be shortened by 10 micrometers since 1 will equal to 1 micrometer, 10 will equal to 10 micrometer. 50 sarcomere will be by 50 micrometer and so on. To shorten by 5 centimeters requires some 50,000 sarcomere to be arranged in a series. How did we deduct that? When relaxed sarcomere is about 3 micrometer long, then 3 micrometer multiplied by 50,000 equals 150,000 micrometer or 15 centimeter, about the resting length of a human bicep brachii. Of course, the changing of the unit we talked about in the previous lecture using the unit ladder and the unit stairs, and how to change it from left to right, adding zeros and taking out zeros according to how many steps you took. I think it needs more. Again, I'm going to repeat that. A single sarcomere is about 3 micrometer long when relaxed and 2 when contracted and has shortened by 1 micrometer. How does this result in shortening 5 centimeter in a human muscle like biceps brachii in a human arm flexor؟ احنا قلنا كل مايكرو فايبر راح يتكون من ساكروميرز مرتبة بالترتيب أو بالتسلسل. بما أن كل الساكروميرز shorten when the fibers contract تتقلص، the length change of each sarcomere لازم نضيفه سوا. مثلا احنا قلنا each sarcomere راح تتقلص ل1 مايكرومتر، فإذا chain من 10 sarcomere راح تتقلص ب10 مايكرومتر، وإذا 50 ب50 sarcomere، وإذا مايكرومتر، وإذا 20 ب20 مايكرومتر، وهكذا. حتى نحسب الشورتنينج ل5 سنتيمتر نحتاج تقريبا 50,000 ساكرومير. لأنه تقريبا الواحد سنتيمتر هو 10,000 مايكرومتر، فإذا هي 5 سنتيمتر راح نضربها في 5 بس عندنا 50 ساكرومير نحتاج نرتبها. بحالة الريلاكس مع كل ساكرومير إذا هي تقريبا 3 مايكرومتر، وللوحدة 50,000 مايكرومتر، فراح نضرب 3 مايكرومتر في 50,000 حتى يطلع عندنا 150,000 مايكرومتر، ونرد نحولها من المايكرومتر للسنتيمتر، واللي راح يطلع عندنا 15. These two questions were talking about the length of the contraction. This one will talk about the speed of the contraction. If the muscle was only 1 sarcomere long and the sarcomere shortened 1 micrometer in 0.1 second, then the muscle could contract at 10 micrometer per second. يعني إذا الساكرومير إذا العضلة كانت عندها 1 sarcomere long وحيصير بيها shortening ل1 مايكرومتر 0.1 ثانية، فهاي المصل تقدر تتقلص عند 10 مايكرومتر للثانية. So this note is for only one muscle. How fast could a muscle 100 sacromeres long, about 300 micrometers total in length contract. B. How fast would a muscle of 10,000 sacrometer long, about 3 centimeter long, contract? To answer this question, the muscle with 100 sacromeres could contract 100 times as fast as 1 millimeter per second. The muscle of 10,000 sacrometer long could contract 10,000 times faster at 10 centimeters. Longer muscles are faster, all other things being equal. Of course, reality is more complicated. There are other factors to consider, for example, the muscle fiber type. Chaining sarcomers together in series increases the contraction distance and hence increases speed, which means longer muscle fibers tend to be faster. Of course, we see it in runners and sometimes soccer players and basketball players because they have taller leg muscle, taller ligaments, they tend to be faster. Force of contraction. We have here four sarcomere arranged in a parallel. The difference of arrangement between the parallel, which is in this state, keep in mind, and this one in a series. Okay? In a series, it means one after the other, one after the other. But in a parallel, one facing the other. Okay? This is in a parallel. Which arrangement generates more force? Four sarcomeres in parallel or four sarcomeres in series? Of course, the answer will be the four sarcomeres in parallel will generate four times as much force in series, as you can see here. If we have, let's like a hypothetical situation, two sets of muscles, one in a series arrangement and the other is in a parallel arrangement. Then the series of muscles in a parallel arrangement will generate four times more force as in series. Okay, now we're going to talk about the skeletal muscle fiber. Based on fiber distribution and based on the functional difference based on myosin isoform. As you can see, this is the basics of skeletal muscle types in humans and in rodents. We have four columns in this table. The color of each muscle fiber, the label, the oxidative state, and the myosin isoform. Of course, the myosin isoform or the myosin heavy chain, its other name, is the motor protein of the big filaments. Okay, it's called an isoform because it suggests that it has different characteristics for different properties of muscles. First, we have the red color of it. The label is called type 1. Type 1 for slow oxidative. Okay, and type 2, okay, so we have the first one is in the color red, also called type 1. Its oxidative state is slow oxidative. And type 1 is for slow muscles, okay, or slow twitch muscles, and that is used for long distance, and they endure more, and they become fatigued slower. In myosin isoform of it, MHC 1 beta, which is the myosin heavy chain 1 beta. The type 2, they are usually in white color in the muscle. They have two types. Type 2A, which is fast oxidative, which is called the myosin heavy chain 2A. The type 2A is fast oxidative for moderate distance, okay, for moderate fatigue. This means that the type 2, which is white colored, becomes fatigued faster than type 1. However, not completely fatigued, in a moderate way. The type 3, the second type of white color, which is type 2B, which is fast glycolytic myosin heavy chain 2D4X. Okay? And this last part is used for short distance but high intensity and becomes fatigued quite fast. So let's imagine these type of muscles. We're talking about leg muscles. Type 1 will be used for walking. Okay? Type 1 will be used for walking because it can withstand long distances and will become fatigued. It will take longer time to be fatigued. The second type, joggers may apply it, or it can be applied to joggers, sprinters, Olympic champs who do fast walking, because the fast oxidative of type 2 will take moderate distance and will be fatigued, but not in the same speed as type 2. Type 2b is fast glycolytic. This will be used mostly by runners for short distance, okay? Because it will have this will have less endurance for slow distance, but it will become fatigued or have a high rate of fatigue. You have here the table 9.2 structural and functional characteristics of the three types of skeletal muscles. We have the slow oxidative fiber, fast oxidative fiber, and fast glycolytic fibers. We have the metabolic characteristics, activities best suited for, and structural characteristics. Let's look at the metabolic characteristics first. We have speed of the concentration. For the slow oxidative will be slow, the fast oxidative and the fast glycolytic will be fast.